Now, in this lecture, we will going to talk about the conductivity in the intrinsic semiconductor. So, when we are talking about the conductivity in the semiconductor, we have already seen that the conductivity is present due to the hole and the electrons in a semiconductor. So, we can write that the in an intrinsic semiconductor, so I will be using a Greek letter sigma. So, I will be writing a sigma I. Okay, so I'm representing it sigma I for the intrinsic, that the sigma I will be equal to sigma n plus p. So I'm referring n for the electron and p for the hole. So the total conductivity in an intrinsic semiconductor will be given by sigma n plus sigma p. Okay, and if we talk about sigma n, so the sigma n will be equal to En into mu n, and sigma p will be equal to Ep into mu p. And we have already seen that in intrinsic semiconductor, number of hole is equal to the number of electrons. That means n is equal to p equal to ni. That means both are same. So I can write conductivity sigma I equal to, I can use this formula like this, that sigma I equal to En into mu n plus Ep into mu p. And since we are writing that n is equal to p equal to ni, so we can replace this equation E ni mu n plus E ni mu p. And I can take E ni common from the equation. So I can get a ni, so E ni in bracket I am writing mu n plus mu p. So what we can say that the conductivity in the intrinsic semiconductor is equal to E ni bracket mu n plus mu p. So this is my formula for the conductivity in an intrinsic semiconductor. Now talking further, when we are talking about the conductivity, we can also talk about the resistivity. Okay, so now we will be talking about the conduction current density present in the intrinsic semiconductor, that is given by the J. So we say that the current conduction density J is defined as the product of sigma I into E. And we have already calculated what is the value of a sigma I. So we can write the equation of a sigma I from the above equation. So I can write E ni into mu n plus mu p multiplied by E. Okay, so we can say that this is the current density of an intrinsic semiconductor. So moving ahead, we can also define the resistivity, which is the reciprocal of the conductivity. So the resistivity we are representing by the symbol rho, and we can write rho I is equal to 1 by sigma I. Okay, so this is the resistivity of an intrinsic semiconductor. Now we have to remember the important points when we are talking about the intrinsic semiconductor. So I'm writing very important points to note. So the first thing which we want to discuss is that you will not going to find that any of the electronics device are being fabricated using the intrinsic semiconductor. Okay, so I'm writing that any electronics device is not fabricated using intrinsic semiconductor. And the reason is that because we have seen in the last slide that the conductivity is constant and we cannot control the conductivity of the intrinsic semiconductor. So the reason is because its conductivity is constant and cannot be controlled. Therefore, we can say that whenever we will going to draw the VI characteristic of this intrinsic semiconductor, it will going to follow your Ohm's law. Okay, so I'm writing that thus the VI characteristics of the intrinsic semiconductor will always follow the Ohm's law. So what we can say is that when we are talking about the applications of an electron device, we say that we require a characteristic which we can control according to our requirement. So we want to get the desired characteristics. Hence, we can say that to get the desired characteristics, we are going for the extrinsic semiconductor. So I'm writing it that we are going for the extrinsic semiconductor to get our desired characteristics. So we are writing that we are going for extrinsic semiconductor, and how we can get our desired characteristic is by controlling the electrons and hole combination. Okay, so that is we are writing that we can get the desired characteristics by controlling the electrons or hole combination in extrinsic semiconductor. That is, we can control its conductivity. So I'm writing here that we can control its conductivity by controlling the number of electrons and holes in a extrinsic semiconductor.